Bye.
Right.
See you later.
See you later. Okay. Hello, everybody. Just going to wait for some more people to arrive. Obviously, we're a little bit before time. We're on Sarah Lisa's channel, so it is, of course, Intro to Statistics. Okay, so I'm just going to wait a couple of minutes for other people to arrive and everybody to settle in a little bit. You should know me by now. It's week 6 of Intro to Statistics, which means you've got one more week until you've got a little bit of a break, which I don't know about you, but I'm excited about. Sounds like somebody is upset in the background here. I think they're going for a walk, so that should resolve itself within the next couple of minutes. All right, let's just give ourselves another couple of minutes for anybody who's a little bit late to kind of drag in. Okay, one extra. Two extra. Okay. Hopefully that's everybody. So it's week 6 of Interest to Statistics. I'm still Jenny. I'm glad that a few of you are still attending. Usually by this point in the semester, it just gets a bit tricky. It gets all a bit overwhelming and everything like that. So I'm really glad that you're still here. The plan for today is to do some of the exercises of sheet 6. I think I tried to do more than I should have done on Tuesday morning. So we're going to just change what we're going to do. We're going to do question 3 because it's going to give us an idea of how to formulate a lot of the other questions. We're either going to do question 4 or question 5, depending on how I feel. And we're going to try one of the final 2 questions because that's a slightly different topic. So let me just switch to the visualizer and we'll get cracking with question 1. As always, I'm going to leave some little gaps for you to try and do the next step yourself. If you haven't had a chance to look at the exercises in advance, those little gaps, they might not be long enough for you. And I wouldn't be surprised if they're not long enough for you. I just want to kind of keep the pace a little bit reasonable for anybody who has managed to try the exercises in advance. And my understanding is that you should have at least tried. Now, certainly when I was an undergraduate, when I was told to at least try before the tutorial, often that involved me reading the questions and going, oh dear. So don't worry if you've not had a chance, but the little gaps, they may not be long enough for you, so you might have to go over the material again in your own time. Okay. That just sounded like I was going to have an intruder for a second then, so I was just making sure everything was going well. Okay, so let's have a look at question 3. So question 3, we were given a whole sequence of 25 separate IID random variables. So n is equal to 25, and for I between 1 and n, we had xi, which were normally distributed with mean 112 and variance 12 squared. And there are also IID as well. So this question had 3 parts. Of course, same as always, just let me know if something is out of focus or if I make a silly error, or even if you've just got a question. No such thing as a stupid question with this material. Okay, so the first part was, what's the sampling distribution of x bar 25? So what we're being asked for is, what's the distribution of the mean of these IID random variables that we're looking at? And we should have a good idea of what that is by this point. So we should know that the mean of the sample is the same as the mean of the underlying population. So hopefully they're normally distributed with mean the same, 1, 1, 2. And we should also know that the variance of the mean of that data is also related to the variance, but we need to scale it. So we need to scale the variance 12 squared by the number of elements in the sample. So I'm going to have 12 squared divided by 25. So hopefully that was just an easy little bit of bookwork to like kind of warm us up. Just noticed there's somebody outside. So, okay. So the second part of the question, we were asked for a probability. So we were asked for, what's the probability that x bar 25 is bigger than 115? And doing this one together is handy because it gives us an idea of how to calculate these probabilities in general. So I want to write this in terms of a CDF first, so that I can look it up in my normal table. So I want to say, the first thing I want to do is I want to switch the direction of the inequality. And I can do that by doing 1 minus. Okay. And then I can recognize that, well, this is a normally distributed random variable. So if I scale both sides of this, so if I standardize both sides, then I'm going to end up with something that relates to the normal distribution. So what I'm going to need to do is this one. So when I standardize 115 with respect to this distribution, I'm going to end up with 115 minus the mean, so minus 112, and then I need to divide by the standard deviation. So I'm going to need to take the square root of this. So let's divide by 12 over 5, because if I take the square root of a ratio of squares, I could take the square root of each one, of the top and the bottom of the fraction. Okay, so I'm going to end up with 1 minus CDF of the normal distribution, and 75 over 114. Okay, and you should be able to just look that one up, and hopefully if you look it up, you're going to get 0.105756, this one. Okay. So part C was only a little tiny bit more complicated than this, but I think the difficult bit, or it wasn't really difficult, but the first step that sort of like got us going was to express what was being asked for in mathematical terms. So we were asked for x bar 25 deviates from the mean by no more than 1. So and we've got loads of possible ways of looking at this. So we could say that the absolute value of the difference between x bar 25 minus the population mean is less than 1. We could say that totally equivalently mu minus 1 is less than x bar 25, which is less than mu plus 1. Now this one is maybe the most condensed one that we could have, but this one here maybe gives us an idea of what we want to be doing with the probabilities. So again, hopefully, if I scale correctly here, so if I make some transformation of each element here, I'll be able to write this in terms of the CDF of the normal distribution. So just really wanted to give you a little bit of a go there, now that you've got this hint as to where to start, so how to express this mathematically. So I wanted to just give you 2 or 3 minutes just to either double check your answer or try and proceed from this point, and then I'll just quickly run through what to do, and then we will move on to question 4. Okay, so we'll just move on. So the first thing I'd like to do is I'd like to standardise this line. So I want to subtract off the population mean, so mu off here and off the middle term. And I want to divide by the standard deviation, so 12 over 5, square root of this term. So I'm going to end up with okay. Now I know that this random variable in the middle here is normally distributed with parameters 0 and 1. So I can write the probability of this guy. It's going to be, because it's an interval, it's got more than one inequality, it's going to be the difference between two CDFs of the normal distribution, because we're sort of taking a wedge. 5 over 12. Okay, and again I can look those up. They should be symmetric, of course. Okay. All right, so we should be roughly there. Okay, lovely. So that's sort of given, hopefully that's given you a little bit of an idea as to what we want to be doing and when we're asked to find whether or not a random variable is less than a point, and also whether it's when our sample mean is outside a certain interval of the population mean as well. So with those kind of things in mind, let's crack on and try question number 4. And I just want to give you really just like a little bit of a hint here. So what I decide to do is I'm going to decide to take two sequences of random variables. I'm going to have some xi's, and each of these is going to be normally distributed 23, and I'm going to have 10 of those. And I'm going to take some yi's as well, and they're actually going to have the same distribution, normal 23, but there's going to be 15 of these. And of course they're IID in both cases. IID in both cases. And the first thing I want to ask is, so what's the distribution of the mean of the x's, so x bar 10 and x bar 15. So y bar 15. And I think that's kind of pretty straightforward. So we'll just go for, maybe while I'm just chatting about it, really, for you to fill those in. So just think about it in the context of the previous question about pretty much everything that we're doing on the course at the moment. And what we've been asked for is the probability that the difference between these two things, so the difference between x bar 10 and y bar 15, so the absolute value of that difference is bigger than 0.3. So hopefully you've been thinking about that a little bit, and hopefully it's apparent that the means are going to be exactly the same as the population means that we're pulling, the properties of the distribution that we're pulling each of the individual xi's from. and that we need to scale the variance in a suitable way. So we're going to have a variance here of 3/10 because we've got 10 elements in the sample, and here 3/15 because we've got 15 in individual random variables going into y bar 15. Okay. So we've been asked for this one. So I've got sort of, I'm pushing us in the right direction, hopefully. And with luck, we can use an idea kind of a little bit similar to what we were doing here to proceed. So I think I'd like to leave you with a couple of moments to do that. You will also need to have a think about what's the distribution of x bar 10 minus y bar 15. My hint is going to be, well, we're dealing with normal distributions. It's still a normal distribution. So have a think about what that is, and then that is going to help you with expanding out this in terms of the CDF of the normal distribution with parameters 0 and 1. So again, I want to give you a little chance to give it a go. Yeah, I'm going to give you five minutes, I think, this time. And then we'll come back and we'll double check we're all going in the right direction. While you're all working on that, if anybody wants to direct message me and just ask something about it, or say, I don't understand, or go quicker, go fast, go slower, whatever it happens to be, just please feel free. And I'm going to stop talking now so that you can actually concentrate. Okay, so at least here, we should be fine with saying, well, it's the difference between two normal random variables. So I need to take the difference between these two means, which is 0. And I need to add up the two variances. So add these two up, which conveniently is a half. Now, the next thing I need to notice is that this inequality is the other way around than the previous question I was answering up here. Here I was looking at a less than, and that's why I was able to put the random variable in between the two values and proceed from there. So the first thing I need to do is reverse that inequality, taking 1 minus. Okay. Now I'm in the situation where I'd like to write this one similarly to how I had it before. Minus by, so I need to divide by the standard deviation of the difference. So that's going to be the square root of a half. Okay. Where z is normally distributed with parameters 0 and 1. So this one here I should now be able to write in terms of the CDF of the normal distribution, which I can look up in the table. This one. I assume that you didn't have enough time to. That's a good question. So Joe's just asked me, why are we dividing by a square root of a half? So what we found is that the difference between x bar 10 and y bar 15 is normally distributed with parameters 0 and a half. Now, the parameter that I usually put in here is a variance. And when I rescale in order to make the random variable in the middle of the inequality, so this thing here, normally distributed with parameters 0 and 1, what I usually do is I divide by the standard deviation, not the variance. And, you know, these are the things that you should be asking, because on Tuesday morning, I actually started dividing without the square root. And somebody was like, what are you doing? And I was like, oh yeah, I need to put the square root on. So it's the kind of thing that you can do if it's too early in the morning, or you just like something slips your mind. So, you know, always ask these things, because there's no guarantee that you know, that it's not something that's gonna, you know, befuddle you sometimes. You know, it's fine. Okay, so you should just be able to resolve that with a table. And you know, if you hadn't given it a chance in advance, I expect that you wouldn't have been able to get around to doing that in 5 minutes. So next one is question 5, and I sort of want to do a little bit of it. I'm not going to do an awful lot of it, but I'm going to give you a hint that will be able to lead you to be able to finishing it off yourself. And the reason for that is that it's also useful for question 10 as well. So we would like to model the number of people in who support A in each of the samples with a random variable. And I'm going to call them X and Y. And they're going to have the same distribution again. So they're going to be independently distributed, but the distribution is going to be binomial. 200 people in the sample, and the probability of success, or the probability that they pick A is 65%. Okay. So Y is distributed exactly the same. We assume that they're independent, of course. Now, I'd kind of like to be able to approximate these binomial distributions with the normal distribution, because that would just make my life so much easier when it comes to calculating. Nobody wants to calculate anything to do with the binomial distribution with 200 people in it. Just, well, maybe with R, but, you know, just really no. So the first thing you want to be remembering is that X is approximately distributed normal NP NP 1 minus P. And if you've done question two gives you an idea of when you can use this representation. If X is distributed binomially with parameters N and P. So the only bit of this I would like you to try and do, because it's going to push you in the right direction to being able to do this, is approximately what's the, how can you approximate the distribution of X minus Y divided by 200? Okay. So, yeah, maybe have a little break and have a moment or so to have a think about what you're going to do with that one. So, I mean, hopefully you guys are thinking that you're just going to apply this line here. And the only thing that might be puzzling you is what to do with the factor of 200 on the bottom. Now, it appears that the mean is not too much of a problem, because if we have the mean of a random variable times by a constant, then that constant is going to be able to move outside the sum in the mean. And the divide by 200 is just going to cancel out with the 200 here in the approximation. The variance is going to be a bit more tricky, because you're saying, well, if I have, if I'm trying to find the variance of a random variable that I've multiplied by a constant, that's of course going to have a square in it, because, you know, of the square in the definition of the variance. So I'm going to need to not only remove this n, but divide by n here if I'm dividing by n here. Okay, so that's sort of what I was hoping that you were thinking of there. Okay. So question 10, I picked this one out because we had an estimator and we needed to find some properties of this estimator. And also we had binomial distribution again. So we had n random variables, each of them binomial m and p. And that's kind of important, that n is how many of them there are, and then each one of them is from a sample of m people. We assume that we don't know what p is. So we've got no idea what the probability of success in the general population is. And we've had this suggestion that we maybe use p hat, which is the sample mean, plus 1, and then all divided by n plus 2 as an estimator. And the first thing we were asked to do is we were asked to find the bias of this. So the definition of the bias that you should be able to remember. So the bias of p hat is the difference between the expectation of p hat and the actual population property, so minus p. Okay. So if you could remember the definition, hopefully you'd be able to calculate that. We were also asked to find the variance of p hat and find out what happens is, so maybe, well, I'll ask you for that one as well. Okay. So again, I want to give you like 5 minutes just to give those a try. And okay. Yeah, so I'm going to give you until the nearly to the end of the class in order to continue to give that a little bit of a go, okay? And I've got somebody on chat, so I just want to respond directly to them while you're working. Okay, so I'd like to give you the answer at least for the first one of these in the final few minutes that we've got together. Just as I was saying in the chat, I just want to offer yet more reassurance that it's okay if you're like swamped with work and you've not had a chance to look at these questions yet, and you come in and then they just get blasted at you at the speed of light and you just think, I just can't keep up, and Miss Sexton's just like, she's only given me a couple of minutes to do this and I'm never going to be able to do this. Like, if that's your thought process on this, like, take a deep breath. It's really common, you know, for it to be a bit overwhelming in terms of the workload. Even though I was an undergraduate a really long time ago, I still do remember constantly feeling behind and constantly feeling like everybody else knew more than me. Just finding that really, really difficult. And often come into class and people were having a conversation about the questions because that was the format that the teachers like to use where I was studying. And I just felt like I didn't have anything to contribute because I just didn't even know where to start with things. And I think that's not that the material is too hard necessarily for you guys. It's just the fact that, you know, you're being asked to do so much and then things back up and you're just like, but I need to have done what I was meant to be doing 2 weeks ago in order to be able to do this. And, you know, and you need that little opportunity of the Easter break to catch up. So you've only got one more week until you've got that opportunity to like sort of like catch your breath a little bit. It's great. Don't worry about it. Please don't worry about it too much. So let's find the expectation of p hat, because hopefully that'll give us an idea that this question is not really as difficult as all that, right? So if I want to find the expectation of p hat, I need to take the expectation of this thing, and it's got loads of constants in, so hopefully I can take those out. So definitely the n plus 2 on the bottom I can take out. And I can take out this one as well, I hope, as well. Okay, so in this case, I've been asked to find the expectation of the sum. So the sample mean, so the expectation of the sample mean when I've got n elements in there. And I know that the underlying distribution is this one. Now I can just replace this by just any one of the x's, because I know that the expectation of the sample mean should be the same as the expectation of one of the identically distributed x's. So I'm just going to pick number 1 because that's convenient to me. And hopefully I can immediately see from the fact that it's binomial MP that this value should be MP. MP plus 1 divided by n over 2, n plus 2. Okay, so the final part of the question that I wanted to cover is we were asked, so what happens when n gets really big to the bias? And at the moment, it's not immediately, well, maybe it is immediately clear that if I stick this in to this expression here and I let n go very, very big, this expectation of p hat's going to be getting very, very small. It's going to be going towards 0, but I'm still going to be subtracting off the p. So as n tends to infinity, I'm going to end up with the bias of the p hats. But this is not nice notation. I don't like this. I think if you're talking about n going to infinity, then there should be explicitly some n's in here. So I would have liked it if there was a little n here, but that's just me being really pedantic. I'd hope that the bias of those sequence of p hats, because I want you to be thinking, no, it's not just one object, it's for each n, it's a different object, is going to tend towards minus p, because this one goes to 0. because the expectation of p hat tends towards 0. So this is going to be a asymptotically biased estimator. So it's not really a great estimator, because for really large n, it gives us completely the wrong value. We'd hope that it gives us p. For really big n, we'd hope that it was sort of like converging on the right value, but actually it's converging on completely the wrong value. It's going to 0 instead. So it's not a great estimator. And you've been asked to do the variance of p as well. Of course, you're going to get the solutions by the end of the week, so you can line up what you've tried and the solutions and go through it like that. Okay. So I'm going to let everybody go. There is 15 minutes before my next class. I've got to take the same tutorial again at 5. So if you want to hang around and ask anything, I'm more than happy to hang around for you to say something. And, you know, if anybody does have the same concern that, you know, that they do feel behind and a bit like this is not helpful, could you just DM me that? Because if nobody says to me, you know, it's not helpful going over the current sheet because I'm just way too behind for that, then I don't know that you guys are behind. Because if I was in Alan Turing building and you were all in the same room as me and I was talking and I was looking around and all of your faces were just like, oh, what? You know, I would be able to gauge that you needed more help. Whereas this way over Skype, it's really difficult for me to tell if you need more help without people directly messaging me. Okay. All right. I'm going to see you in 4 weeks' time because of your break. So have a really nice break and I'll see you in 4 weeks. Hello, welcome early birds. You're so early that I even had myself on mute. Nice to see you all. Although it's a little bit metaphorical. I'm certainly going to wait for everybody else to arrive. So just settle in for 5 minutes or so and I'll be back. Hello, welcome to everybody who is on time. This is our latest room, so we should all be clear that it's intro to statistics. Yeah, it's week 6 and you have to suffer me again. You're all on time. So I'm going to give anybody who's running a little bit late a couple of minutes to get here, and then we'll crack on with some exercises all together. Okay, let's get cracking. And somebody's even said hello, which is really nice because usually people just say goodbye or thank you. So keep it up. Let's all have a chat all of the way through the class, not just at the end. So the first thing I want to say is thank you for still coming and thanks for holding on in there at week 6. I might be getting disturbed. I'm going to try not to get disturbed. Yes, I'm getting disturbed. Okay, so yeah, that was really distracting. Anyway, what I wanted to say was, you know, somebody highlighted in the previous class that they didn't feel that it was very helpful because they felt like they'd got really behind and they didn't really know what was going on anymore. And if you are in that position, first of all, thank you so much for continuing to at least try and turn up. And secondly, remember that probably a good proportion of the other people here feel exactly the same as you. Although it was a really long time ago, I still remember how overwhelmed I used to feel as an undergraduate by the time the middle of the semester had got here. I was usually about 1 or 2 weeks behind with the notes. Often I couldn't even get started on some of the questions on the exercise sheet because I just wasn't really too clear about what we were meant to be doing. And it's not easy. And sometimes that's okay. So if you have any questions and you feel like they're silly, ask them anyway. And if you don't feel bold enough to ask me, ask your friends, ask Sarah Lee's. You can ask in class or you can email outside of class. And I really just want to encourage you to just hang on in there. It's 1 week until we've got 2 weeks off. And that will be a little bit of an opportunity for you to review what's happened so far and really try and at least get your head around the ideas that are going on. So pep talk over, it's time to crack on. So the plan is, I'm going to get interrupted again. But the plan is that we're going to do question 3 because it's going to give us an idea of what kind of formulation we use for all of the other questions. And then we're going to do question 5. And we're going to do question 5 because I've been trying to do question 4 and 5 and just running out of time. So I'm going to do question 5 and then we're going to do question 10. And the reason for doing those 3 is because we just see a little bit of techniques that we can use for the other questions. Okay. Oh, lovely. We've got 2 highs. Hi. Yeah. Anyway, so let's switch over to the visualizer. Okay. So question 3. What were we asked about? We had a sequence of 25 random variables. And we know that they're independently identically distributed. I'm going to index them with I. And each of those xi is distributed, it's normally distributed with parameters mean 112 and variance 12 squared. Okay. So the first thing I was asked was a little bit of bookwork. You should have just been able to look this up, which was what's the distribution of the sample mean? So what's the distribution of x bar 25? So the mean of all of these x's that I've been given in the question. Now, a key thing to remember is that it's a normal distribution. So x bar 25 is going to be normally distributed, and the parameters are the mean is the same as the mean of the xi's. So the mean should be 112. And the variance needs to be scaled by the number of elements in the sample. So the 25 that I've chosen. So I'm going to have 12 squared divided by 25 as the variance. Okay. So the next part, I was asked to find a probability, and this is kind of handy for us to know how to approach this type of thing going forward. So I was asked for what's the probability that x bar 25 is bigger than 115. Right, now my goal is to write this beast here, this probability, in terms of the normal distribution with parameters 0 and 1, so that I can look it up in the table. Now I know that I've got parameters here which are not 0 and 1. Oh, I've got 3 more people. Okay, so welcome to everybody who's managing to just come in just right now. We're in the middle of doing question 3. We're looking at what the probability that x bar 25 is bigger than 150. The first thing I want to do in terms of writing it in terms of a CDF is do 1 minus to change the order of this inequality here. So 1 minus the probability of x bar 25 being less than 150. Now here, I've got a normal random variable on this side, but the parameters are not something I can look up in the table, so I want to standardize. So the first thing I'm going to do is I'm going to subtract the mean off both sides here. And I'm also going to divide by something. Okay. So what I want to be dividing by is not the variance, so not this number here, but the standard deviation. So I have to take the square root of this guy. I'm going to end up with 12 over 5. So it's something where I made a mistake in the very first tutorial I did this week because I was just hurrying through the question. I forgot to take the square root, so I put 12 squared divided by 25 here, and somebody pulled me up and said, hang on a second, you're meant to be dividing by the standard deviation, not the variance. And in the previous class, again, somebody asked me the same thing. So where's the square gone? Where's the square gone? So just be careful when you're standardizing, you divide by the standard deviation, not the variance. And for this one, I'm going to end up with 1 minus the CDF for the normal distribution, and I'm going to have to evaluate at this. So 15 divided by 12. Okay. And overall, I should get myself to 0.1056. Lovely. So for part C, the key thing I need to be able to do is I need to be able to interpret what the question says in terms of a line of mathematics that I can put into my probability. So what I was asked for is x bar 25 deviates from the mean mu by no more than 1. Okay, so to write this as one line of maths, I mean, you know, one thing I could write would be like the absolute value of the difference between 25 and x bar 25 and the mean, population mean, which is 112, is less than 1. Or alternatively, what I could say is that -1 is less than that difference. and the difference is less than 1. So this second one is maybe more helpful because I can immediately see that it's going to be a little bit like this one in B, isn't it? But this one, I've got an interval rather than, well, an interval that doesn't go all of the way to infinity on one side. Okay. So I want to be able to try and find the probability of this guy. And to be able to do this, I want to rewrite it in terms of the CDF of the normal distribution. So that's the first thing I'm going to give you to do. So I'm going to ask you to, can you carry on? So if we write -1, x bar 25 minus 2 less than 1. Can you write that in terms of the CDF of the normal distribution? You might have, with parameters 0 and 1, you might have to do more than one step to get yourself there. And I'm going to give you a couple of minutes to give it a try. I'm always happy to hear feedback. And the other thing to bear in mind is that I'm not going to give you too long for these little breaks. So again, if you've not looked at the exercises in advance, which is totally fine, you've got loads of courses on and I realise it's difficult. You know, don't expect to necessarily be able to do all of the steps in the little break I give you, because I'm just trying to keep the pace good to get through 2 or 3 questions. So I'm going to stop nattering because it must be really distracting. Okay, so Lewis is asking why I do the double line on the P, and it's a bit optional. It's just the word processing kind of program that we use to like write our thesis in and that type of thing. People either do like a bold P for a probability, or they do a double line P for a probability in the way that they typeset. And it's really, really unnecessary, but it sort of like just makes them like pop out of the page at you. And it's kind of like, I guess it's one of those little quirky things I do. So feel free to just use a P if you're used to just using a big P. Yeah, well, I like it too. I like it too. And, you know, it sort of goes with the double line I for indicator function. So, you know, I think it's nice. Okay, so I think the first thing I want to do to this thing is maybe if I divide by the standard deviation, then that random variable in the middle is going to have a different distribution, isn't it? So why don't I try that first? So I want to divide by 12 over 5. Okay, and now I've got minus 5 over 12 is less than z is less than 5 over 12. And z is a lovely standard normal distribution with parameters 0 and 1. It's good, right? Okay, so from here, I can use the CDF of the normal distribution. And I should be able to just proceed from that point to get myself a numerical value. Numerical value is going to be 0.3234. So hopefully you managed to get yourself to that point. So the next one we're going to try together is going to be question 5. And I sort of want to start you off a little bit. So we had 2 separate samples and we had a percentage of people who were going to be supporting candidate A. So in the first sample, I'm going to say that the expected number of people supporting candidate A, or of the actual value of people, the actual number of people supporting candidate A in sample 1 is going to be X, and that X should be binomially distributed with parameters 200 and 0.65. So there's 200 here because there's 200 people in that first sample, and 65 because we think there's a 65% chance of them supporting candidate A. So that's the number of people supporting candidate A in the first sample. And I'm going to have Y, and I'm going to have that independently distributed exactly the same for the number of people supporting A in the second sample. So. Okay. So the next part is maybe a little bit of a leap, and I'm going to use a result which was on one of the exercise sheets for probability 1, which was about approximating the binomial distribution with the normal distribution. And you've also seen this in question 2 if you've had a chance to look at the exercise sheet. So if Z is distributed binomial at NP, then I can say X is approximately distributed normal NP, and the variance is N times P times 1 minus P. And you should have seen in question 2 and also in the lecture notes that this is a good approximation for certain values of N and P. So the first thing I'd like you to try and do is write down for me what the distribution of, so what's the distribution of X over 200, Y over 200, and X minus Y over 200. Okay. And I'm going to give you a couple of minutes to take a look at that. If you've already done it, or you're racing ahead and you manage to think about what those are within the time that I give you, could see what you would like to do moving forward. See if you can continue on with the question. But I'm going to give you a few minutes and come back, and then we'll do that bit and continue from that point. I should, of course, say approximately. Because I'd like you to think about what kind of how we could approximate them with the normal distribution. I should have been more clear about that. That was what I was after. Okay, so it's difficult for me to watch whether any kind of cogs are whirling because I can't see you all because we're still all over Zoom. So I'm going to crack on. So x divided by 200 is going to be approximately distributed. We know it's exact. We could have an idea of its exact distribution because we know what x is, right? What the exact distribution of x is, but we know that it's approximately distributed with the normal distribution, and the parameters would be, so how would the mean of x be affected by us multiplying by a constant? So I'd have to multiply the mean by the same constant. So here I'd have, I know that n in this case is 200, I'd have the n outside. So the n that I'm dividing by, cancelling out this one, I'd end up with a mean that was equal to p, so it was equal to 0.65. And then for the variance, if I think about the expression that I've got for the variance, if I have a random variable multiplied by a constant, then the variance of that new random variable that's been multiplied by a constant has to be divided by the square of the constant. So again, I'm going to have this format for the distribution of x, and then I'm going to need to rescale because of the divide by 200. So 200 times 65. 1 minus p is going to be 0.35, and then divide by 200 twice, so 200 squared. Okay, now this one and one of these are going to cancel out. Okay. Now, hopefully, we're okay with the fact that y divided by 200 is going to have exactly the same approximate distribution because we knew that x and y are identically distributed. What about the difference? So if I take the difference between the two, so I'm taking the difference between two normal random variables. I take the difference between their two means, so 0.65 minus 0.65 is 0. And then with the variances, I need to add them up. So so hopefully you got those out. Okay. So pulling my page down a bit. What the question was actually asking for was, what's the probability that x minus y divided by 200? So that's, oh, sorry, on the top of the page. So x minus y divided by 200 is the percentage that the two samples, the number of people supporting A in each of the two samples differs by. And we were asked that this is less than 10%, so less than 0.1. Okay, now hopefully you can see a similarity with what we did for question 3. So with question 3, I had the absolute value of a random variable being less than 1. and I manipulated it in order to write it in terms of a difference of the CDFs of the normal distribution. So again, I'd like to give you a little bit of a chance to carry on. So I'm going to give you maybe till 12:30, just to double check what you've done if you've already worked on the exercise sheet, or to give it a go for yourself. You know, writing out this in terms of the CDF of the normal distribution. Don't worry if you don't have time to actually look it up in the table as well. Okay, so I think the first step of what I'd like to do is maybe get rid of the absolute values. So go for two inequalities instead. Now I can't jump immediately to the CDFs of the normal distribution because I know this random variable in the middle has a variance which is not equal to 1, so I need to standardize. So I need to divide by this standardizing factor, which is going to be the square root. And I've got it down as 0.002275. And what this is 0.65 times 0.35 divided by 100. 7, 5. So that's what's been got. That's what's going to be going on these on the bottom of these fractions to standardize. And that's got a bit messy, but it's the same factor on all of them. Okay, and now I've got this thing in the middle. I can define it as Z, which is distributed normally with parameters 0 and 1. So I'm nearly ready for the CDF of the normal distribution. Yeah. Okay, so I'm going to end up with 0.1 divided by this crazy square root, 0.002275. And the same on the other side as possible, minus 0.1 divided by the same factor. Okay, and you should be able to look that up in the table, and you should get yourself to 0.9640 by the table. Okay, so that's going to leave us about 15 minutes for question 10. So question 10. For question 10, I've been given some binomial random variables. So I've got a sequence. I've got n random variables in that sequence. And each of them are IID. Xi is distributed binomial with parameters m and p. Now, this is kind of important that n is the number of random variables I've got, and m is the number of random samples being taken, that's behind each one of the xi. So in terms of the total number of trials, that's huge. That's going to be n times m, total number of trials. Okay, so we've been told that we don't know what the probability of success is, so we don't know what p is. And we're given a possible estimator in the question. And the estimator we're given is p hat, which is the sample, the mean of all of the samples of each of the elements in the sample, so x bar n plus 1 divided by n plus 2. And the two parts of the question, the first of all, to find the bias and to discuss what happens when n tends to infinity, and also to find the variance and discuss what happens when n tends to infinity. So we'll start off by doing the bias together. So if you want to think about the bias of p hat, we know that by definition this is the expectation of p hat, so the expectation of the estimator, and then we subtract off the population value, the p that we don't know. And ideally we'd like this to be really small, we'd like this to be 0, hopefully. So to calculate this, I'm going to need to take the expectation of this guy here. And hopefully use some of those rules we've been talking about, about what happens when we've got constants. So I'm going to ask you to not only do that one, but I'll also ask you to take a look at the variance as well. So what's the variance of p hat? So if I took the variance of this term, what would I do with the constant on the bottom? What would I do with the constant that's being added on there? And I'm going to give you another 5 minutes to give those a crack, and we'll come back and go through, and hopefully we'll have time to talk about what happens when n gets really big as well. Now, one thing I've been saying to all of the other groups is I'm not 100% sure about this notation, because if I'm going to be sending n to infinity, I sort of want to recognize that each of the p hat depends on n, that for each n there's a different p hat. So maybe I would want a little n here, indicating that for each n there's a different p hat. So that might be something that's been bugging you or confusing you a little bit. But yeah, there is a dependency between the estimator and the n in question. Okay. So again, I'm going to stop babbling, give you 5 minutes to work on it. And if anybody wants to DM me and just say I'm stuck, or, you know, tell me what the answer is, and just be like, yeah, it's too easy. You know, whatever you want to say to me, please feel free. Okay, so let's crack on. So I asked you to do a lot in 5 minutes there. Again, don't feel too upset if you've been unable to finish. So let's start off with the expectation of p hat. So to find the expectation of p hat, I need to take the expectation of this guy. Now, everything there except for x bar n is a constant, so it can come outside the expectation because of linearity of expectation. So you can just take everything else out. And we've used this over and over and over again, that the expectation of the sample mean, so of x bar n, is the same as the expectation of any of the xi's. So just for convenience, I'm going to write the expectation of x1. Yeah, just because, you know, I could have taken any of them, but I'm going to take x1. And the expectation of x1 in the case that we've got binomial distribution with parameters mp is m times p. So we should have mp plus 1 divided by n plus 2. Okay, so with that in mind, my bias is then going to become m plus p, so mp plus 1 divided by n plus 2 divided by p. Okay. So what's going to happen to this beast here, so this bias, as n tends to infinity? So as n gets really, really big, n plus 2 is also going to get really, really big. So this fraction here should get very, very small. So this term's going to go to 0. And this term's going to stay the same because it's got no relation to n. So I should have minus p asymptotically. So I'll just write it out again as a statement. So as n tends to infinity, the bias of p hat is going to tend towards minus p. Now, what this means is that this estimator is asymptotically biased. So it's not a great estimator because for large n, the expected value of p hat is going to be really small. It's going to be clustered around 0. But we know that the actual parameter p is probably not 0 because it's a binomial distribution. It would be trivial if it was 0. So this is not really, it's given us an idea that like p hat is maybe not the best choice of estimator. And regarding the variance, if I take the variance of p hat, again, I need to consider what happens when I take the variance of something with some constants in. So I would have the variance of, I need to write out the definition of p hat. So I'm multiplying by a constant there. The constant's 1 divided by n plus 2. And if I want to move that outside the variance, I need to square it. Okay. So the variance of a constant is 0. So I can just get rid of this term, one would hope. And the variance of x bar n in this case, what's it going to be? It's going to be the variance of one of the xi's divided by n. So let's deal with that. Yeah. So that's my rescaling factor, and then I've got the variance of any one of the xi's, so one of the xi's, and I know that this thing here is m times p times 1 minus p, because I know that they're binomially distributed. Okay. Okay, so the final thing we were asked was, oh, so what happens when n tends to infinity to the variance? Hopefully you can immediately see that if n gets really, really big, the only thing it's going to affect is the numbers on the bottom of the fraction, which are going to get very, very large, which makes this get very, very small. So hopefully you can immediately see that it's going to go to 0 as n tends to infinity. So in terms of the variance, p hat is an asymptotically consistent estimator. So it's kind of like the type of estimator that we'd really quite like. But overall, I think the fact that we've got this issue with the bias is going to outweigh the fact that we've got an estimator which is asymptotically consistent. Okay, that's it. So we're just going to wrap up for today. I'm going to hang around maybe for a few minutes just to answer any additional questions, but it doesn't seem like anybody's got any because we've been quiet up till this point. I'm actually going to see you in 4 weeks rather than 2 because of the break. So have an absolutely lovely Easter break, and I hope you get to really relax and not think about stats for 2 weeks. Okay. Thanks, everybody. Okay, Han Tao, Jaylee, and Jinyu, do you have any questions, or shall we all go? Oh, you too. Have a lovely day. Okay.